we are continuing with the milestones, right? This type of prototype. We have just discussed that this is a type of prototype which will be more physical, more tangible, and which will prove to the customers and to the suppliers and so on that some milestones have been achieved. So now a summary, right? A summary of relevance of prototypes in various purposes is shown in Exhibit 8 on the next page. Here is steps in rapid prototyping process: creation of a solid model, conversion to STI file, rapid processing, model validity, repair slicing, product prototyping, post-processing, and so on. So these are the actual steps which we will do later on, right? Which we will do later on. So here, if you see Exhibit 7, alpha and beta prototypes of the PAC robot, right? So you are now trying to demonstrate to the customers that this PAC robot can travel on staircases, on steep hills and slides and so on, right? And Exhibit 8, appropriateness of different types of prototypes for different purposes: learning, communication, integration, milestones, right? So when we have a solid, it is more appropriate. When we have hollow, then this is less appropriate. Note that fully comprehensive analytical prototypes are really rarely possible for physical products. So if you see focused, analytical, good for learning, but these are analytical only, right? So to communicate with customers and so on, they are not very good. Focused physical are good for learning, good for communication, but not these. These are only focused. Comprehensive physical is of course good for learning, good for communication, good for integration, good for milestones. So these are different types of prototypes. And you see, we took a product as an example, a PACbot, right? So this is a very high level product in one sense, that the army and the police will be using this type of robot in some dangerous conditions where they don't want to send their police officers and their army officers or workers, and they are remotely operating this and so on. So it has, it should be able to take military fire. It should be able to take very different types of temperatures. It should be able to move on normal roads and in deserts and in hills, and this, it should be able to climb into buildings, right? So it is a very good example of a complicated product. Therefore, because it is a good example of a real product in a very complicated scenario, therefore they have the luxury of having a lot of money and having a lot of resources. So they can do prototyping of different types. But if we have a smaller project, then we may do only a very simple type of cardboard or foam prototype only to discuss with the customer that this is how it will look like. But we don't have enough money to play around with. So we say, okay, now you agree that this will be the shape and so on. Let me go ahead with the product, right? So it depends. But these are all the different types of prototypes for different uses, right? For learning, for communication, for integration, for milestones. So the principles of prototyping now. Principles of prototyping. There are 5 principles to decide which type of prototype to build and how to combine the prototypes into the development project plan. Principles only. Some ideas that what type of prototype should I make and how should I integrate this prototype making into my design and production. Principle 1. Analytical prototypes are more flexible than physical. For example, a stall torque of the PACbot motor. Torque and stalling torque. It's a very mathematical type of an idea, right? Varying torque and then solving the equations is much easier than changing the actual motor in a physical prototype. You know that there is a motor. Each motor is for a certain torque. It will produce this torque. So if you want to change these motors in the real physical one, it will be very complicated. But in your equation or in your simulation, You can change the torque and see. So analytical prototypes are more flexible. You can do a lot more changes at the analytical level than in the physical level. Physical prototypes are required to detect unanticipated events, right? If it is going over staircases, then what will happen? Now it is very difficult by equations to predict it, right? As an example, pull test of various pegboard gripper finger coatings. The gripper is there, the fingers are there in the gripper, the coatings are there. So what will happen when we will pull them at different loads by different forces and so on? It is very difficult to do analytically, right? But physically you can do it. So the team discovered that some of the coatings with good grip characteristics had poor durability. That gripping, right? So you have to coat with something. If this is this type of paint, it will not be good for gripping. If this is this type of paint, it is good for gripping. But this one which is good for gripping, when we do some tests, then after a few tests it failed. So it is not durable. It is good for gripping, it is not durable. So these type of things you cannot do with equations, right? So one principle, another principle. Third one, prototype may reduce the risk of costly iterations, right? Iterations mean you do it once, you do it, you have actually, right, you make the product and then it fails. So you come back all the way to concept design and this and that, and then you start changing the concept or start changing the detailed design and so on. Iterations, remember. So prototype may reduce the risk of costly iterations. Of course, if a molded part fits poorly with its mating parts, the mold tooling has to be rebuilt, right? You are making some parts and they have to fit together and there is a mold, right? So in exhibit 9 on the next page, 30% risk of returning to mold design and building after parts fit testing is represented with an arrow labeled with 0.3 probability and so on, right? So if you do some prototyping very early rather than late, then you know that, oh, right now if we change the mold design or do some other things, then we will be much better rather than discovering it 60% later in the work. You know, from the beginning we have been telling you in the course that if some defects, if some errors are earlier detected, then the cost is very little. But if the errors are detected late, then the cost in terms of cost and time and effort, all time, effort, cost, all that cost increases, right? So this is the third principle of prototyping. The benefits of a prototype in reducing risk must be weighed against the time and money required to build and evaluate a prototype. This is important for comprehensive prototypes. So you see, now there are two things. If a prototype is there and because of the prototype you have detected some errors in the product, then you will save a lot of time and effort in the actual product. But building the prototype is itself an effort and cost and time. So the cost and time and effort used in building the prototype, is this important? Should this be done to find the errors, or this making the prototype itself, the comprehensive one, is itself very costly? So this is a big decision for the design team and the management to make. Sometimes you may decide that no, we will find all the possible errors through simulations. Making the physical prototype is very costly. But it depends, right? We always say, are you building a Kia car? Are you building a Corolla car? Are you building a Rolls-Royce? So when you have a customer who is very particular about quality, but they say, we can give you higher cost, no problem, then we can go for very costly prototypes so that our product later on is very good. But right, so these decisions are always limited. So here in this exhibit, a prototype may reduce the risk of costly interaction. Taking time to build and test a prototype may allow the development team to detect a problem that would not have been detected until after a costly development task, such as building an injection mold and so on. So process with prototyping and conventional process. Build the injection mold. Some parts, plastic parts, are to be injection molded, so build the injection mold. Test the part, that does this part fit with the other one. There is 70% probability of success, but there is still 30% probability that it will not be a success. So this is big, right? That 70% of the times it's okay, but that 30% of the times when the part does not fit, so you go back and change the mold. So now the cost is very high. But with prototyping, build prototype part, test the part fit, and then build the injection mold, actual injection. So now if it does not fit, which there was 30%, but then you are changing only the prototype, and based on the prototype you will change this, because here you are building the prototype based on which you will build the actual injection mold, isn't it? So here, if this 30% happens, if it does not happen, you will go there. But if this happens, you will only change the prototype, and now the prototype has passed. So now you will build the actual. So in this case, now when you test, there is 95% chance that there will be success, and only a 5% chance that you will have to go back, right? So having the prototype really improves your chances of success, but it adds the cost of the prototype. So this decision is always a tricky decision for the design team and the management. Exhibit 10, the use of comprehensive prototypes depends on the relative level of technical or market risk and the cost of building a comprehensive prototype. So here, cost of prototype, low cost, high cost. Here, technical or market risk, low risk, high risk. So this one prototype may be used for verification if the cost for prototyping is low and if the technical or market risk is low, right? But risk is low, we can go for high cost. So you see, few or no comprehensive build prototypes. See, here we are saying that this is car, computer, right? And these type of things, projectors, but we are building a ship. But so even if the risk is low, then making a prototype is a huge cost. So maybe we don't build any comprehensive prototype, or we build very few, right? But if the risk is high, and the cost of prototyping is low, then we can build many comprehensive prototypes. So softwares, packages, food products which are low cost food products, right? So because the risk is high, if anything goes wrong, then a lot of backlash from the customers can be there. But the cost of the prototype is low, so you can do many prototypes. Now here is dangerous area, right? The risk is high and the cost of prototype is high. So in this case, some cars, some aeroplanes, you do some comprehensive prototypes only, but you definitely do it, because though the cost of prototyping is very high, but still the risk of not doing is very big. So this type of chart, right, with cost on one side and risk on the other side, is a very good type of study to do to decide how many prototypes you will actually make or not make.